Okay, very good. Let's do that. Um, and before I actually switch screens, I'd just like to say to everyone, Happy Hanukkah, and also to let you know that Paula is going to become a new member of my class, I can call it, or my group called Pathways to a Sustainable Planet, and I will be sending him very soon um, a schedule for next spring. It starts in late February and goes through until the end of April, or 10 lectures. And I think of those 10, um, 3 of them I'll be giving. I have about 3 or 4, I think, guest lectures, and then we have some group discussions. But of the 3 that I'm giving, I think 2 of them might be very applicable to your group. And so I will pass that along to Paul, and maybe sometime in the spring, late spring or so, I can come on again if you're interested.
Yeah, thank you.
Okay. All right. Now let me share the screen then now. Okay. And I'm going to shrink those of us who are on the side there. Okay. So here it is, December the 10th. And the title is Advanced Reactors, What They Are and Why We Need Them to Save Our Planet. That's quite a statement, that second phrase, but I hope to get that across to you. First of all, there are 2 kinds of nuclear energy. There's fission, where you're breaking apart large atoms, and fusion, where you're fusing small atoms. The typical small atoms that you hear about are hydrogen and helium, and that has some advantages over fission because there's less radioactivity generated, less waste that might be dangerous. And so people have been wanting to see fusion, work for quite a long time, and it's always very, very difficult to achieve. It's basically making the sun, what's going on in our star, manipulable here on Earth and controllable. We've done that for a bomb, but we haven't been able to do it in a controlled way. And that's very sad, but maybe someday, I don't think within the lifetime of any of us, but maybe it will be practical to use and low cost enough to supply our grid, but I doubt it. On the other hand, fission is has been around since World War II. Of course, it helped to um, finish off the war against Japan, and there are various theories about that. The about the ethics of that. People were consulted, the scientists at Oak Ridge, as to whether or not there should be a bomb dropped off Tokyo Harbor, and would that convince the emperor or not. And most of the people at Oak Ridge voted to do that rather than bomb cities in Tokyo, in Japan. But uh, the president at the time decided that, he said the buck stops here, and he took the responsibility, and he felt that we had uh, to make a more impressive impression on the Japanese to get them to surrender, and that was his choice. But I think it has given fission a bad name and a lot of fear, and a lot of it is from ignorance. We think of the bomb in relation to controlled fission. And the picture there on the left is an example of controlled fission. What you see in the center is the nucleus of a uranium atom, and around it you can see faint blue arcs, and those are the electrons that are spinning around the atom. It's a large atom, one of the largest um, of our natural elements. It has an atomic weight of 238, and there is an isotope that is a smaller version of it that is 235. 235 one is the one that is fissile. That means it will spontaneously uh, fracture or fission, and but it's decayed over the years since the Earth was formed, and so there isn't as much of it as there used to be. Of the uranium that's mined, less than 1% of it is 235. And so it has to be enriched, and that's the basis of the conflict that you hear about with Iran because they're trying to enrich it more than we would like. Generally, to be anywhere in the legal end of dealing with uranium, you cannot enrich it more than 20%. Most of the uranium that goes into our fission reactors is enriched no more than 3 or 4%. And we only allow it to decay, or it can only decay about a couple of percent, and then we have to refuel it. And that happens about every 18 months. If we put in a higher concentration, as they do in some of the rockets they'll be sending into space before too long, those will be a much higher enrichment and they will last a lot longer. There is talk about enriching some of our small reactors in the future up to 10 or 15 or even 20%, and those will last a lot longer before they need to be refueled. What you also see there are 3 intense yellow lines. Those are neutrons that are released at the time of the fission reaction into 2 smaller elements. And sometimes there are 2 and sometimes there are 3. It comes out an average of about 2.5. And those neutrons have a lot of energy, and I'll explain that to you a little bit later. But that energy is quite powerful and releases a lot of heat, and the amount of it is determined through Einstein's equation E equals mc squared, where you take the slight loss of mass of the reaction, that is, the 2 fission products are slightly lighter than the original material, and you take that tiny difference in mass, multiply it by the square of the speed of light, and that's the amount of energy released from each fission reaction. So it's a very, very energy dense form of energy. And you'll see in the background some other little atoms fissioning, and that tells you that in order to have a lasting source of energy, you need to have fission that will spread to an adjacent atom, and that's called a chain reaction. And Enrico Fermi, when he came here from Italy to the University of Chicago, it took him 2 years working for President Roosevelt under the Manhattan Project. It took him 2 years to find a way to make the fission into a chain reaction, something would happen. So it's not an easy thing to do. We thought that the Germans were busy making them, and it turns out they were, but they were not nearly as smart as Fermi and some of his workers. And so they were way behind us. So we didn't need to worry too much, but they were working on it. Anyway, that's the story of, on the left side, of fission. And now let's get into the real heart of the matter and what advanced reactors are and why we need them. So we'll start with that next. And I'll just get my little pointer here going. First of all, I'd like to point out to you 2 things. On the left, we see that people are very favorably impressed with solar. You notice 84% there in the top green bar are favorable towards it and only 8% unfavorable. And as you go down through them to wind and natural gas, you see less enthusiasm. But nuclear, really, to my amazement, is way down almost as bad as coal. Now, coal kills, and it's dust from coal kills many millions of people around the planet. And nuclear doesn't have any of those effects, and yet it has such a bad reputation. And I think it's due to the association with the bomb and the unnatural fear that we have. On the right side of the slide, I'm relate again a little bit to the power of the pellet. Before I related to E equals mc squared, but here is an easier thing to understand. These little fuel pellets are about a centimeter long and about 3/4 of or 2/3 of a centimeter in diameter. And just one of these pellets is equivalent to 17,000 cubic feet of natural gas, or 149 gallons of oil, or an entire ton of coal. That's a lot of fossil fuels. And so if we're going to leave those fossil fuels in the ground, obviously we're going to need some oil and perhaps a little bit of gas to make plastic and other things that we have to have, various other forms, rayon and materials and things like that. But in order to leave most of that material in the ground, particularly coal, we're going to need something that's as energy dense as nuclear. And one of the themes that I'm going to talk about for the next few minutes is why fission is so much more important. And I'm turning to this little table that I talked about with Paul over the last couple of days. It's a table made by Wade Allison. He's a retired professor of physics from Oxford University. And he made the interesting quip, we turned left instead of right. And in the central column there, you see under the heading chemical or electronic, he's talking about fuels such as oil, gas, and coal, or food. I mean, we take corn and we take sugar cane and we make it into alcohol and put it in our gasoline. We send biofuels in the form of wood chips from the United States, Canada, and Brazil in vast quantities to Germany, because Germany has made a promise that they would use renewable energy. And as they shut down their nuclear plants, the cost of their energy is going way up. They can't get enough of it from wind and solar. And so they burn our biofuels and just make things worse. And they think they're doing the right thing. But it's unfortunate that they're convinced that they're doing the right thing, but they're not. And coming to the second line, we see under that central column that these fossil fuels and so on derive their energy from photosynthesis or sunshine way back in geologic time. And you go to the next line and it's energy density in kilowatt hours per kilogram. And you see that we're talking about roughly a kilowatt hour of energy per kilogram of coal or gas or some of the fossil fuels. And if you want to have enough energy to provide an individual on the average for a whole lifetime, that includes the Western world, the Eastern world, and everybody on the planet, it averages out to about 1,000 tons for a lifetime. And its advantages are it's reliable, it's available 24/7, but the big problem is its emissions are huge. You do kill some people with gas explosions, as we know, and from oil fires and so on. So, and coal sludge, which is terrible, terrible waste product. So it has some problems, particularly with regard to the climate. And we can see climate change happening. There are many things that contribute to it, but the biggest of them all is making electricity and heat for making steel. All those things are using coal and various other fossil fuels, not just electricity, but when you combine them all together, it's about half of the carbon emissions that go into space and alter the reflection of heat from the sun and trap it here are due to making electricity and energy from fossil fuels. So what we did was we turned to the left and we went to this column called renewables. And people thought, well, it's a nice term. We can use falling water, wind, and sun. And it's just, daily coming in. We think of it as being free. But gee, we go down about 3 orders of magnitude. That's about 10,000 fold in terms of the energy density. We just get a little drab of energy per kilogram of material. I've had solar panels on my roof for the last 11 years, and I've watched them very slowly degrade in their ability, but they've never made very much, especially from well, even in the summer, they only make energy from about 10 in the morning until 2 in the afternoon. But now in the wintertime, on a whole day, a nice sunny day like today, I won't be able to make a kilowatt hour. And I've only got 2 kilowatts of panels on the roof, 10 panels. So, this is 4 or 5 months in the wintertime when I'm not making much energy, and batteries are not going to last for a whole winter, no matter how good they get to be. So that's a problem. And then, of course, you need 10 million tons, not just 1,000, but 10 million. That's 4 logarithms more to have enough fuel for your life. And what they don't tell you in this table is that all of these solar panels that we put up on our rooftops or wind turbines that we put on the hillsides, and I love the look of them. I'm very much enamored by both water, wind, and sun. But they don't tell you that these things only last Well, the dams last for about 50 years or more, perhaps 60 or 70. But the solar panels, mine are starting to go after 11 years. By 20 years, they're going to be gone, and that's what everybody else finds. They say that people think they'll last 20 and then stop, but they start to degrade well before 20 years. And the same is true of wind turbines. They never last, to the best of my knowledge, beyond 30 years. They just deteriorate as they're going round and round in the cold and rainy weather, and the fiberglass simply doesn't hold up. So they're very popular. They're very well accepted. But what people don't like to talk about is they're unreliable. They're weak. They damage nature both by um, damaging birds and bats in particular, which are wonderful mammals that keep down our insect population and mosquito population. But but more than that, we haven't even thought about recycling solar panels. It's a Wild West attitude in America. At least in Europe, they're starting to think about ways that they can recycle them. We used to ship them off to China, but China last January said, no thanks, we won't take any more. So sooner or later, we're going to have to start thinking about it, because these solar panels that we keep putting up all around the place are going to run out of steam. Pardon my use, not really steam, but energy production within 20 years. Now we come over to the far right. This is where we should have gone, but because of our fear, these fuels, uranium and thorium, which are two of them, they came from pre-solar stellar collapse or supernova. They're much, they don't exist on our star, but they're in the planets that surround our star because they come from the stellar, interstellar dust that accumulated into the planets that revolve around our sun. And the energy density is 20 million kilowatt hours per kilogram. So very, very much more. And you can see when you compare, looking across that table, the differences from turning left toward renewables and turning right towards nuclear. What a huge difference. We're talking of 8 or so logarithms. I beg your pardon, that's, let's see, about 7 logarithms to go to the right and losing 4. So that's about 8 logarithms difference. I'm sorry, 11 logarithms difference going from the left column to the right column. Huge, huge difference. So we're really putting our enthusiasm that the Sierra Club used to think it was a good idea, and people thought no, and they actually split the Sierra Club fighting about it. And those who were opposed to nuclear won. And so now the Sierra Club gets a lot of money from big oil industry, because the oil industry is terrified of nuclear and wants us all to think that it's terrible, so will continue to burn fossil fuels. So nuclear energy then is reliable, safe, compact, resilient, and available 24/7. The big problems are public apprehension and failed education. So what they don't talk about, and the press doesn't bother to mention, they say, well, up in the upper right-hand column there, they say, well, 20% of our energy comes from nuclear, globally only about 10%. What they don't say is that over half of all carbon-free electricity in the United States comes from nuclear. It's the carbon-free that's in the denominator, and only then, when we get rid of when we wipe out the fossil fuels from the equation, do we realize that a vast amount of our carbon-free electricity comes from nuclear. And we don't seem to recognize that, nor do we recognize the health and environmental benefits that we get from people who are well-trained who run these plants. These people are paid well. They have a lot of revenue, about $450 million a year buying local goods, and nuclear plants pay a lot of taxes. So we shouldn't be too critical of nuclear, even from the economic aspect. I want to just touch on a couple of little quickies here. On the upper right, it's a rather small table, but the operating time, I wanted to point out, if you look at the percentage of the time that the solar panels are generating energy, it's 27%, wind 35%, coal 53%. Gas, I think, should be a little bit higher than that, but perhaps it's because it's used as a filler for solar and wind that it's artificially dropped. But the point I want to make is that 92% of the time, nuclear plants are running, and that's a big advantage. And in the lower left, we see that since 1989, and this is now 30 years, we've made so many improvements and upgrades in how nuclear plants operate that we've lost a few plants. But in spite of that, over the 30 years, it's equivalent to building 32 more nuclear plants, even though we haven't built them, because we're making them more efficient. Nobody bothers to tell you that. You never hear that from Bernie Sanders, who says there's too much waste and that sort of thing. He means well, but he should get educated about nuclear before he tries to knock it. And I'm so glad that he's not our president-elect. Joe Biden, at least, is much more knowledgeable and interested in supporting nuclear energy than Bernie Sanders ever will be. I like Bernie for many points of view, but nuclear is not one of them. Well, getting on to our nuclear fleet, it is aging because we discovered them. And so you see there, the red bars mean plants that are over 30 years old. Yellow is 10 to 30, and blue is less than 10 years. So we haven't been making plants for quite a while. I'm going to show you a few that we have been making. And it's understandable. The good news here is that these 10 to 30-year-old plants have got a lot more life in them. They were built with the plan to run for 40 years as opposed to 20 or 25. And most of them are getting renewed for another 20 years, and some of them for another 20 years after that. So I think it won't be long before we have nuclear plants running for 80 to 100 years. So they're much more, and that factor, that difference in age, is not factored in when people say, well, nuclear is too expensive. They don't factor in the fact that they're around for a long time, whereas the renewable energy is not. The European Union is similar. And as you go to some of the other countries, ending up with China, China's been so busy building coal plants that they don't have many old nuclear ones, but they are building them now, as well as as some coal plants. Unfortunately, they're really desperate to make energy as people move into the cities and make more and more products for us.
I got a question for you on that last slide.
Yep.
I see a little sliver of blue right at the beginning of United States on the far left side. Have we opened a nuclear plant lately, or where'd that come from?
Just hang in there. It's called VOGTLE, VOGTLE, and I'm going to show you. They just got the fuel today, so your question is well timed. The VOGTLE, they have two reactors there, 1 and 2, which are the old-fashioned kind, water cooled, and these are bigger water cooled ones. I'll show you pictures of that in just a few minutes. I wanted to touch on nuclear shutdowns. There are several different reasons. The ones you see here in the green are plants that have been shut down a while ago, and they are called ISFI, that is Independent Spent Fuel Storage Installations. They've not been totally decommissioned yet, but they're in storage, and the fuel has been separated from them, and they're in a very safe place. I'll get back to how safe in a few minutes. If you look into the next group, you can see one here from La Crosse, Wisconsin, is still being decommissioned. Zion, Illinois, Vermont Yankee, and so on. I'm going to touch on Crystal River in a little bit to show you exactly what I mean by that. Kewaunee has more recently been shut down, but fortunately, the other remaining reactor in Wisconsin looks like it's going to be around until 2050 or beyond for another good 30 years. These are going to be shut down soon, these two in Illinois, and it's too bad. I'll show you a picture of the Byron plant in a few minutes. But Diablo Canyon, I'd be very sad if that were ever shut down. The governor of California wants to keep it going, and I think he is going to find a way, but it'll be difficult. But I think when people continue to have these rolling blackouts in California, they're going to realize that if they shut down their last nuclear plant, they're going to be in big trouble. So hopefully they'll see the light. This is an interesting map because it shows some of the closed plants. They're marked in deep blue. What gives me joy from this slide is that there are 10 nuclear plants in light blue. And those were the ones that were reversed. They thought they would close them because of competing reasons. The utilities buy these up. They're privately owned, which is kind of good and bad. If you go to France or many other places, the government at least controls and has an influence to keep these things from being sold willy-nilly from one utility to the next. And when they think that they can make some money by investing on the money that's there to decommission them in other things while they're waiting for them to cool down, they get sold off, and eventually They replaced them with natural gas or methane plants, which is really a shame. But these 10 plants, they realized that it was a bad decision when they looked more carefully at the economics. And a lot of that was led, excuse me, by a guy by the name of Michael Schellenberg. He actually ran for governor, though not many people know that, but he's a strong nuclear advocate, and he formed a group called um, Environmental Progress, and he helped, I think, was active in all 10 of those reactors that were reversed and are staying a while afloat for a while. The problem is that you cannot keep these old-fashioned reactors going forever, even if they're made well. They're still accumulating some waste. They call it waste, but it's not. It's just inefficiently used fuel. There's a lot of energy left in it, and it can be used in the new reactors that I'll be telling you about shortly. This is an example of a decommission going on in Crystal River. And these are pictures. You can see the times here. Starting now for the next 7 years, they're going to be decontaminating and dismantling the plant. Then for the next 10 years after that, they will continue operating, not for making energy, but just for maintaining the dry cask storage, which I'm going to show you in a minute. And then after 2037, they're anticipating returning it to this pastoral landscape. I'm not sure if that'll ever happen, but I'm hoping that it might. This is, I'm trying to think of the name of the company that's doing this. Anyway, it doesn't matter. Exelon, I think, put up this from their website. I'll show you more about that in a few minutes. These are the nuclear waste locations. Now, when Bernie Sanders said there sure is a lot of waste, he's right, but it's just not really waste. This is unspent fuel, and some of it is in important places. These are important sites. Hanford, of course, is where a lot of weapons were made up in Washington. Idaho National Laboratory is a laboratory from the Oak Ridge, and so on. There are other research facilities, Department of Energy sites where some of it is stored. But these blue circles are simply commercial sites where they're developing energy now. They're active. Palo Verde plant, for example, in Arizona is not on the water. They use air cooling. But Diablo Canyon is still generating a lot of good energy. They're still running, but they stored their waste, which is not that much compared to coal. It's 1/1,000th the amount, but it's still there and potentially dangerous if it were allowed to be spilled or put in some inefficient way. We need to be honest with the public and explain about these closures. This is what they look like. These casks were loaded at the beginning 34 years ago in 1986. They're made of stainless steel with a coating. They've been dropped from heights. They've been smashed into moving trucks. They've had all kinds of horrible things done to them. They're still doing studies on the duration of the stainless steel and whether there are any salts in this waste. There must be some. And they want to know how long it would take to corrode, because 34 years is not very long, but they'd like to know, because we don't know how long before advanced reactors will use up all this fuel. This is potential fuel. They can burn it all. And when we get these new advanced reactors going. And so we shouldn't rush them all off to Yucca Mountain. They're perfectly fine there. They've never hurt a flea, let alone a person. And they're now at more than 60 sites in 34 states. And so they're quite safe. We just should learn to know how long before they might start to leak a little bit, and we should start planning to make advanced reactors so that we can start using that material. Just a last idea on the fear problem. Fear does dominate our opinions, not only thinking of weapons, but we're thinking of people stealing it. And I remember Barack Obama said one day, one of his worst dreams was that some bad people should get a hold of nuclear waste and then put it in a conventional bomb and just blow up someplace. It may be his worst dream, but we have to look at the history of 60 years of nuclear energy and look at the number of people who have died per 1,000 gigawatt hours. And look, it's tiny. It's 0.07 of one death per gigawatt hour. And look at all the other sources of energy we have. So our track record is very good. And we have to owe some of that to a rather cantankerous fellow um, who was very, very safety conscious, Admiral Rickover. He had very, very safe nuclear navy, far safer than the Russian Navy. And he was asked by Eisenhower to build the first nuclear plant on land, and he used the water reactors that he had experience with in submarines to build the first nuclear reactor in the United States in Shippingport, Pennsylvania. That was three years after Russia accomplished it in Russia, and Eisenhower was pretty ticked off that Russia beat us to the draw. But at least Rickover built one in 2.5 years, and it's still operating to this day, although I think some of the other plants are being shut down there. There's several reactors. Anyway, I really should point out to you what these generations of reactors are. Here along the bottom, we see these definitions: generation 1 in the lower left on this red bar, generation 2. Basically, the generation 1 are these original ones, Shippingport I mentioned, and some of these were in the Chicago area. Then we have the term LWR. That's an acronym for light water reactor. And there are two kinds. You can either pressurize the water or you can boil it. If you boil it, you only have it working at 100 degrees Celsius. If you pressurize it, then you can bring the temperature up to 300 degrees plus. The Canadians like to use deuterated uranium, and so they call it CANDU for Canadian deuterated uranium. And then the Russians have some other initials back there, but those generation 2 reactors are basically what's been in use for all through the 70s and 80s and 90s. And then we started making some bigger ones, and that's the one in Vodal that I'll show you about. These are called advanced reactors, but they're still light water. So they're only advanced in the sense that they're not so dependent upon the electric grid to keep cool. They've built some systems into them so that they're bigger, perhaps a little less it's supposed to be less costly to operate, but unfortunately, because of delays, they've ended up being too costly. One of them, the European pressurized reactor, has a checkered history in Europe. And then we come to this vague term, generation 3, sort of plus. And these are basically, we're going to talk about them in a little while. These are the small modular reactors, and they act as a bridge to get us into the generation 4. And I'll discuss these in detail shortly. But just before we finish these old-fashioned reactors, here's a picture of the Votal one that you were asking about. That's in Georgia and or South Carolina. I've forgotten which state. They're very close to one another. There's a summer one there, I think in Georgia maybe, that hasn't done so well. This one perhaps is in South Carolina. But it is anachronistic in design. It is expensive, and fuel utilization is still low. It's the old-fashioned water reactor. And they said units 3 and 4 will not run before 2021 and 2022. And this is 3 over here, and that's 2021. And today they got their first delivery of fuel. That cover that you see there, of course, was taken over a year ago. And that should be up and running by next year. So what about the European pressurized reactor? Well, it's another form. Areva and EDF and Siemens, 3 huge European companies, international companies, got together 20 years ago and put together this design of the EPR. Some of them are running, but many were canceled because of the delays and the increased costs, as you can see on the second point there. The pictures that you see at the bottom are underneath each one. The one in France that's famous is Flamanville. The one in Finland is the middle one, and the Hinkley Point one in England. Those are all just starting to come online soon, but with enormous delays. And here's an example of the delays in France. The open circles you see on the left are the time of announcement. The filled circles are the time when they think they might be commissioned, and they gave it about 5 years from when they first started planning the first one in 2007. And you can see that they had to change it, and they made some changes as they went up into the colors. And those colors are defined over on the right here with these different years. And you can see they went right up until last year. And even last year, they're planning, not last year, back in the teens, about 2018 and 2019. And now they think, well, maybe by 2022 we'll have it finished. What I want to point out also is the cost. This is demonstrated in the ordinate here, and you can see that the cost is almost tripled um, over this time. Well, this big machine is still being upgraded. There are delays, and the delays have enormous costs as they try and make it perfectly safe and from any possible earthquakes or anything like that. However, in Belarus, as you know, it's not a very democratic country, in fact, not democratic at all. And so when the premier there ordered 2 units from Russia, they just popped them in without worrying the public about it at all. And they're now up and running. You can see where Belarus is in Eastern Europe there, not far from Russia, and Ukraine, where they had Chernobyl accident in 1984. But the people said, well, if the government says it's okay, they'll believe him, and so they do. And they, although they don't believe him on many other things, anyway, these 2 units provide 1/3 of their electricity. So they've cleaned up. These countries, particularly Poland and Germany, are the biggest polluters in Europe. They have coal plants that just emit the most horrible air pollution because they burn lignite. We don't have as much lignite over here. We have some in Pennsylvania, but most of the stuff we ship in every day from Montana is a much tougher form of coal that doesn't make so much pollution and so many particulates. Anyway, that's another aside. So how did 4 other countries get ahead of us? Look at Russia here. They're, when it comes to new reactors, they're coming. 37% of the world's reactors are coming from Russia. Another 28% from China, Korea, and France are ahead of us. And yet we started it all. Well, how is that? Well, it's because of their cost. We haven't been very effective at keeping the cost down, our fear, and our politics. Fortunately, although it should be an apolitical thing, I think the Democratic Party, for the first time in 20 or 30 years, is now behind nuclear for the first time. And I'm glad to see that. So it's becoming apolitical. Both parties are supporting nuclear energy, and I think that will pass in the coming administration. Okay, enough of the old-fashioned light water reactors. I'm now taking you in to the small modular reactors. Some of them are based on light water. Some of them are based on the new generation 4, which means liquid metal of some kind. And so we'll define that a little bit later. But within those 2 mechanisms, the key to the small modular reactors is that they're smaller. Instead of making them to be 1,000 megawatts of energy, and you can think of a megawatt as a windmill. A windmill is typically 1,000 watts of electricity, typically. And some of them are a little bit more, some of them are less, but they average out about that. So if you want to think of the typical nuclear plant, it would be equivalent to 1,000 windmills, or wind turbines as they call them sometimes. So these are less than 300. So they're less than 1/3 the size of a conventional nuclear reactor. What's so cool about them is 2 things. Number one, they don't have to be dependent upon electricity from the grid to keep them cool. It's all done by natural convection and evaporation. The other thing is that they're small enough to be mass produced in a big factory and shipped by truck or rail and assembled on site, and that can reduce enormously the cost. So here's an example of one made by a company called NuScale, N-U, and then S-C-A-L-E. And this is a picture of one. It's all underground so far, and it's the size of 2 school buses, end to end, packed upright on their noses. So that gives you a rough idea of the size of these things. You can see the containment vessel with the blue line there, the reactor vessel deeper in, the steam generator, and then at the bottom, the nuclear core. So these are small. They're modular because you can mass produce them offsite, and they cool themselves by natural convection without needing pumps. Now, this is a better view. You can see it over on the left here, lower left, and there it is underground. The ground level is about here. And these red pipes are the steam, which go up and turn the turbine and generate with this axle the electricity from here, and it goes up there. And this is a vent to keep everything cool. So this generates in this area here, the steam turbine generates the electricity. And here we have what's on the surface from NuScale. Here's how NuScale is spelled. And this is an engineer drawing, and you have the reactors here underground and the electric lines coming across, and you can put, from this drawing, there's 6 of them on one bank and 6 on another bank. So you can have 12 total in this facility. And you can have the, over here are the um, turbines generated on the 2 banks over here. And then the artist came along and said, well, we can make that look a little bit better, put it beside a river and put some trees around it. So that's what NewScale has done to make it a little more appealing. Now I'm showing you the difference here between the Byron plant. Some of my colleagues came up and they put on a demonstration showing exactly how they got into trouble at 3 Mile Island and what they now know. And they train everybody in this place. This is a training facility in Illinois. And they show them how they can avoid ever having that experience again. And everybody who operates a nuclear plant in the United States goes through this extensive training, which they have on site at most of these plants. I show it to you because it shows these old-fashioned relay switches and various things like that, and very few gauges, just a few little computer screens. And that's the way they're still operating, and they're trained to use it well, and it's very safe. But NewScale proposes that you can use less than half as many people in a room and be monitoring much better all those turbines. That dozen or so reactors that are underground are being monitored here in this lower image. So much more safely with fewer people, highly trained. So then comes along Rolls-Royce. You've heard of them, of course, and their cars. Well, they're getting into the business too, and they've thought of a jazzy way to make these things. They're a little bit bigger, 400 megawatts. And look at the thing, it's incredible. It looks like a big cocoon. And you can see the wires coming out from the left here, but it's very much along this design. You can see where the nuclear island here is in this location, the turbine island here, and the cooling water pump house and all the rest of it, the parking and the offices, etc. So it's kind of a way, but they're very optimistic about providing nuclear energy for the entire world, but they collaborate much with many other universities and industries in England. And this is their prediction for the energy profile of the future out to 2050. And this orange coloring is nuclear. And look at the black down here, that's coal. And they're going to have that, they hope, shut down within a decade. And it's going to be replaced by gas for a while. But even the gas will be cut back, and they will use what's called gas CCS. That stands for carbon capture and storage. And that's going to be a bit of a challenge, but they predict that within 10 or 15 years, they'll be doing that effectively. There's still some offshore wind and other things up here in the UK that are providing energy, but it's one of the few things where I've seen people be optimistic about the future. The UK has really done quite a job. And as you know, they're not only getting their vaccines already, but they're moving ahead with nuclear with enthusiasm. Anyway, there's one country that's done it, and there's nobody else but the Russians who have actually built a small modular reactor, and they've had it going for quite a little while, a couple of years. It's been running since last year. It's floating. It's the only one that's floating. It's the only one in the Arctic. Provides power for 200,000 people in Murmansk, and it's been moved up into the Arctic Ocean to provide energy for people who need it for, unfortunately, oil exploration or from various other industries along the Arctic Ocean. But it's refueled instead of every 18 months, every 5 years. And it has a water-cooled reactor, so it's the old-fashioned type, but it has lots of enrichment so that even only every 5 years has to be refreshed, and the whole thing should last at least 40 years. So I show you this table because this is what I had when I gave this lecture 6 months ago to my Plato group. That's about all we had, and most of them were, well, you can see there's the floating one that we just saw in Russia, and this one was just getting approved. So we said near future. None of them finished yet in the United States, and this one in China under construction, and the one in Korea coming along nicely, in Argentina, and this is an underwater one in France. So these are all planned. Well, 6 months later, and look what we have: 6 classes of small modular reactors. There's the water-cooled land-based, the water-cooled marine-based, high-temperature gas-cooled, fast neutron spectrum, molten salt, and micro-sized in the Aurora model. So there's just a lot happening just in 6 months. It's incredible. And the many of the organizations, including our own Nuclear Regulatory Commission, are enthused and are working to get these approved as quickly as possible. NuScale has just been approved, and they're going to start building it out in Idaho. So this is a picture, if you wanted to see where these things are. These are 24 of them, just land-based cooled reactors around the world. Here are the micro reactors, the fast reactors, molten salt, marine-based, and high temperature. So things are really happening, and that's why I'm optimistic about the future of nuclear energy, because things are moving ahead, and the regulatory people seem to realize that if we're going to cut our carbon emissions, the only way we can do it seriously, we can make all kinds of pretty looking wind turbines, and I love them. I like to look at them. I fly an airplane. I like to see propellers moving around, but to leave the coal in the ground, to stop shipping it by train 24/7, day and night from Wyoming and Montana, we're going to need to build some of these plants. These are what they look like in various countries, in Europe on the left, Asia in the center, and Africa and North America. Just quick ideas of the different shapes and designs. We're going to need to get together a little bit more, perhaps, on not having too many different ideas at once, but at least the regulatory commissions will sort that out. Well, just to mention a couple of other things, because these little reactors that are underground have so many more protective layers, you don't need to have such a huge emergency planning zone around it as you do for the traditional reactors. There's a lot of cost to making sure that these are out in the country, and then you have to have all the wires, so there can't be any cities very near them and so on. And even around Chicago, they're all 10 miles out of the center of Chicago in Northern Illinois, and now we're going to be able to put them in. No reason why we couldn't put NuScale reactors in lots of places in Wisconsin. Also, we're thinking about not only producing electricity, but producing heat. And you can see here the petrochemical industry, desalination along the ocean fronts for making enough water perhaps to help them in California to reform oil and gas. They're going to still need some of that to produce hydrogen. And there's a lot of talk about hydrogen as a new substitute for batteries. I don't think they'll substitute for them, but they may be able to help them out a bit for producing ammonia, for farming, and various other things. So there are a lot of advantages of using these small modular reactors in this fashion. Now, I'm going to move now from the small modular reactors to the Generation 4. These are the really neat ones, and it started way back with our old hero, Enrico Fermi, who came from Italy to the University of Chicago in 1942. And he hired this Canadian fellow, Walter Zinn, and he was the pioneer working for Fermi and under his supervision, but really considered one of the most brilliant physicists and engineers ever. He was really a nuclear physicist at Oak Ridge, and he in Chicago, and he supervised the building of the EBR-1. Now here's the EBR-1. Now have a table of all of the international fast reactors. These are the fast reactors that use the energy when it's just coming out of a fission reaction. And the EBR-1 was operational for 11 years, and it was using not water, but sodium and potassium. Those metals, when they're hot enough, they turn into a liquid. And the nice thing about them as a liquid is as they get hotter and hotter, the atoms come further apart and they self-regulate themselves, because as the atoms get further apart, the fission reaction slows down a little bit because they're farther apart. It takes more energy to get to the next atom. And still self-regulatory property is very handy and very safe. Russia immediately got into it, and they had a mercury one, and then they went to one with sodium, and so on. Britain got involved with sodium and potassium combined. And then most after that used sodium. Russia, for their submarines, used lead bismuth. It's a wonderful combination. Lead by itself is good, but you can moderate some of its negatives with bismuth, and that makes a great reactor. The French got involved, and they've had theirs going for decades. Some of them, this one in Japan didn't work very well. And so some of them but these are research reactors. I'm not talking about many commercial reactors. Most of these are not. They're research reactors, but what's interesting is that we've got 25 um, of these things. They've been used over 400 operating years, and I think it's impressive. So when somebody tells you that Generation 4 is a new thing, you say, no, no, it goes way back to the beginning of it all. And here is one of the most key slides I'm going to show you. It is the difference between sodium fast reactors and their energy spectrum of neutrons is shown here. They come into the thing at an energy of electron volts times 10 to the 7th. And they're only scaled down about tenfold before they're used in the sodium fast reactors. So we don't lose much of that energy. But when we were thinking about using water for Admiral Rickover, the people at Oak Ridge advised him not to use sodium because it reacts pretty negatively and explosively with water as well as air. And so they advised him to use water, light water. And so he did. And so this is where he's using the energy. And it's about a million, 10 million times less um, energy in those neutrons. And so they don't all get fissioned. Only about, well, they go from an enrichment of 3.5% to 1.5%. So only 2% of the uranium in the fuel gets spent. And then the rest of it just sits there and in storage. But if they had used these reactors, which have been experimented on in the previous slide, I've shown you all over the world, then it all gets spent. So this waste isn't really waste at all. It's simply unspent fuel. And that's the most important point I'd like to get across in this talk, is that when we move from small modular reactors, as we merge that technology into Generation 4, we will have not only compactness, but we will have tremendous efficiency and be able to burn, literally burn in the sense not of oxidation, but of nuclear fission, harvest all this vast amounts of energy from the stuff that's just sitting around. So in summary, the LWR or light water reactor compared to the sodium fast reactor uses a faster neutron, higher fissile density, much higher fuel burnup, higher temperature, 800 degrees centigrade, but atmospheric pressure. You don't even have to put pressure dome around these things. And they just work so much more efficiently. So how many different types of Generation 4 systems are there? Well, we've just been reading a little bit, mostly about sodium fast reactors. I touched a little bit on the lead-cooled reactors used in Russia primarily. There's another group called gas-cooled. I won't pass on that. They use helium. But I am going to tell you about molten salt because this, I think, is the coolest of the 6. And you use salts here, either chloride or fluoride salts. What notice I want to bring to your attention is that these are closed. What do I mean by closed in terms of the fuel cycle? It means that it's reused, and you can keep reusing it until all of it is consumed. We made the decision a long time ago that it was a little cheaper not to bother to recycle a material. And so that's why we've had so much accumulating as waste. And that's why the public is so upset about it. And it's too bad that for that slight lowered cost, we got ourselves into this quandary, and we all feared about nuclear waste. And it's all because we made the wrong decision 30 or 40 years ago. But what's so good about molten salt is that it's also in that closed fuel cycle. And also you can use, as I'll show you later, thorium, which is 3 times more plentiful in the Earth's crust than uranium is, and you don't have to enrich it. So it's a very useful nuclide for generating a lot of energy. And this is an example then of how a molten salt reactor works. It's what are we doing here in time? Gee, 4 o'clock, I better move along. We use it as a liquid dissolved in a molten salt. We reprocess the fuel. Here is the tank here, and we can reprocess it continuously. There is a xenon gas, which is a nuclear poison and inhibits the reaction and avoid that happening. We don't have to stop things or shut them down. We can continuously harvest the xenon out this tube and even continue some reprocessing here of other materials. And the other cool thing is that there is a freeze valve here. If for any reason the system, which has some electricity going into it to keep the pumps operating, if for any reason that should shut down, this frozen plug will melt, and the all of the fluid here in the molten reactor will pass down into a large holding tank where it'll be so dilute that everything will stop and cool underground. And so that is a large safety factor. Also, the waste from it is much less, 100 pounds or a half a square foot for 30 years. And you can also makes less plutonium waste, which is handy since we don't want to have plutonium as we used to when we made bombs. Also, it throttles down automatically because it's so fluid, and it has higher temperatures, and so it's more efficient, and it can be fueled, as I mentioned, by either thorium or uranium. These are an example of 7 companies, all busy. You notice that Bill Gates is one of the leaders for TerraPower. I'll mention him later, but there are others. Thorcon is a very important company run by Lars Jorgensen, and I enjoy emailing him from time to time and finding out how his company is moving along. They're working hard with Indonesia to replace some of their coal plants with nuclear plants there. And this is another example of Thorcon. They bought a shipbuilding company, very experienced in making ships, and they can put these reactors, 4 of them, inside the ship and deliver them to Indonesia quite efficiently. So this is based on technology that's been around for a long time, and they can combine it with low-cost shipyard. And the idea behind this is they can use these shipyards to mass produce a lot of these reactors and ship them efficiently 4 at a time to companies and utilities that have, particularly in a part of the world, such as Indonesia, where they want to get back into nuclear more rapidly. They may also do this in Japan and other parts of Asia, possibly even Australia, which at the moment is starting to wake up to the fact that they can't keep shipping coal around the world, even though they have a lot of it underground. So I've been talking a little bit about thorium, but I couldn't resist putting in this little joke. This woman, I guess, is having a date with a guy. Maybe he's from Oak Ridge or something. I don't know. He says, "I'm sure you're a nice man, but I'm not interested in hearing about thorium." These 2 books were written by people who are very, very good. This is a scientist at Dartmouth University, wrote a wonderful book. And Richard Martin is a journalist, a science journalist, who also wrote a fine book. So when you hear people talk about thorium, it's not the reactor, it's the fuel. The molten salt reactor is the reactor, and the 2 happen to go together very well. You can use thorium in other kinds of reactors, but it's especially suitable for this combination. Now I'm going to just take a few minutes to compare nuclear energy with renewables that we hear so much about. I've touched on it before, but just look at the capacity factor. I've mentioned before that nuclear is going all the time, as opposed to these other forms of energy, wind and solar. But look at the number of square miles needed to make 1,000 megawatts. That's 1,000 wind turbines or 1 nuclear plant. And you can see that you need a lot more land, as well as having inefficiency here. Also, people say, well, there's an awful lot of cement goes into a nuclear plant, concrete, I mean, and some steel. Well, that's true. But when you look at it per, yeah, there we are. If you look at the mass of material in tons per terawatt hour, not a megawatt hour, but a terawatt is 1,000 megawatts. So that's a lot of energy. You'll find that solar, for all its innocence, really uses up a lot of steel and a lot of cement and other products for a terawatt hour. I just barely make a kilowatt hour here at my house. And so a terawatt hour is an awful lot more energy, and I'd have to have an awful lot more solar panels on my roof. And that's why that graph looks like that, as opposed to this little small amount per terawatt hour of nuclear energy. Another thing to mention that I've touched on before is that when we put the uranium fuel and we load it up into a reactor that is presently working, these light water reactors, we only put in about 33% of it is in this enriched form. And 97% of it never gets used because it's 238 and it doesn't isn't burned with the water moderator and water coolant. And so when you empty out the reactor or do the refueling, it's lost a little bit of the 239 because some of it was converted to plutonium. But 97% of it is still reusable material. And that's what's sitting in these so-called waste containers. And that's why we should not send it to Yucca Mountain, even though that was shut down for political reasons. Yucca Mountain can be useful for some other things that cannot be reutilized. But most of the so-called waste sitting around at reactors that I showed you in my first slides can be reused and should be reused. Also, we're going to need some electricity for the electric cars of the future. You've heard about them, I'm sure. They're going to be used more and more. And here's an example of one fueling up at a Tesla plant. We're going to need some electricity, preferably cleaner than what we have in Wisconsin today. And so we need to plan for nuclear reactors to provide the extra power needed as we switch from the internal combustion engine to the electric motor for our transportation. Now, just touch a little bit on the idea that if we start to fight the renewable people, I think we'll just waste a lot of energy and get nowhere fighting, because we both want to get rid of fossil fuels. So this is a picture, an architect's picture of these wind turbines, and they're working together with some solar panels, and they're redefining the whole idea of nuclear energy. They're designing them to be simpler, more rapid construction, and to integrate with renewables. And the way they're going to do that is by having molten salt. Now, this is not radioactive molten salt. The plant is elsewhere, but once the heat is generated, it goes into storage in these molten salt tanks. And then they can, TerraPower, the Bill Gates group, and General Electric Hitachi reactors are working together to have the salt heated up to high temperatures and stored. And this can be used in tanks so that the nuclear reactor can be making, let's say, 35 megawatts at a particular time for a particular locality in the grid. And then they'll just hold the load evenly, but after it's ramped up in energy, and charge these tanks with hot molten salts. And then as you need more energy in the afternoon, they'll ramp it up to the peak load, coupling the stable energy, because nuclear reactors, you can't turn them up and down that easily like you can a hydro plant, or even to some degree a coal plant, or mostly a gas plant. So the big disadvantage people have been saying about nuclear reactors, that they're not adaptable and they can't follow the load. Well, you can if you use these salt tanks, and you can have the stable nuclear reactor generating the same amount of energy, but you can use the stored heat in these molten tanks of tanks of molten salt. They're not radioactive, they're just holding the heat, and they can be used to ramp up in the evenings and then cool down in the afternoon. So this allows—
comment. So these molten salt tanks are essentially doing the same thing that, say, a capacitor would do in an electrical circuit, or
yes,
maybe a battery. You kind of charge them up and discharge them and even out the load.
Absolutely, and much cheaper. Now, we're not talking about storing energy for months, but it will store daily very effectively. Yes, good question. Yeah, so here we are almost at the end of the talk, just making some points. We want to downsize the small modular reactors. That's what we're doing, from 1,000 megawatts, as we've been using for the light water reactors, to 300, so that they can be mass produced and reduce the cost. We can combine the small size of the Generation 4 reactors, and the most efficient of those is the molten salt. We can combine that small size of the small modular reactor with the efficiency of the modular salt reactor, and you get the two working together. So we've been saying that nuclear had its era back in the 60s and 70s. We think that in the 20s, it will start to, in 30s, there'll be a new era where we combine nuclear energy with renewables. We assist even propulsion into space. People are talking about using nuclear rockets instead of fossil fuel rockets with oxygen and fuel. If we do decide we have to go into outer space for some reason or other, we can integrate steel production instead of burning coal with nuclear energy, and we can desalinate water if we're low on water. So a lot of things in the future. This is a picture here on the right, is a micro reactor, and that's even smaller and almost like a nuclear battery. So if we can get rid of our fear, we can help fix poverty, as many parts of Asia want electricity and don't have enough now, and we can fix the climate. And the only way we can do those things is in that sequence: fixing fear, fixing poverty, and at the same time, fixing climate. I put up this website called rethinkingnuclear.org. It's one that I built with Margie Kindig, a good friend of mine, and Phil Carlson, retired radiologist. And that is up and running. And a lot of questions that you might have If I don't answer them now, you can examine this website. If you look under these things, why nuclear power, facts, and so on, you can find those. So happy to answer your questions, and I will revert to the stopping the share. Okay, hi there.
Is there a regulatory agency as part of the United Nations?
No, the regulatory agencies are divided up by country. So we have our own called the Nuclear Regulatory Commission, and every country has its own regulatory thing. United Nations will give guidelines, and there is an International Energy Association destined to help people who want information around the world. So that's international. But the actual regulation has to be left up to the country because they want their own sovereignty. And people would not want to give up their sovereignty.
That picture that you showed of
I
the
have a
drawing
question.
of these SMRs, and you had like, you know, a self-contained unit. How many of those would you use, or would it take to provide all the electricity for Wisconsin? Are we talking about lots of them, or a few big ones, or a lot of little ones?
Well, you can remember that each one is 300 megawatts, and they can build a dozen of them at a time. So in that one drawing that you saw, so if you multiply 300 by 12, you've now got a pretty big plant, bigger than the average light water reactor, that would be putting out 3.6 megawatts. And no, I'm wrong on that. 3.6
How many of those would it take to run to power Wisconsin?
Yeah, okay, I'm coming to that. I have to work up the math. I can't do it instantly. So you'd have 3.6 gigawatts. Now, I don't know how much energy Wisconsin uses, but if that one plant that we've got up there now in Two Rivers, or is it Two Rivers? No, it's Point. I think it's something Point. Anyway, it's putting out 1,000 megawatts, and it's producing a small percentage, about 7 or 8% of Wisconsin's energy. So if you multiply that by, let's see, 12 or so, you would have it. So you have 12 reactors like that, and if it's only one, let's say 30 of the 30 300 watt things, but 30 since you can put a dozen in one location. It would only take 2 or 3 of those if you had 12 at a time. The beauty of them is you can put in as few as you want. You can put in 1 or 2 or 3 or whatever. And so, for example, you would not have to have so many wires.
Say, instead of putting them all in one place, if they're scattered around,
Exactly.
you don't need so much transmission wires.
Yeah, you'll lose 10% on the transmission. And it's a shame to lose that. Plus, you also lose 10% by storing it, and another 10% retrieving it. And so, so that's not very efficient either. I think that batteries are good for cars and trucks that go short distances around Los Angeles, and that's going to be the wave of the future. But we need. I think the small modular reactor gives tremendous versatility, and Puerto Rico is a classic example. That island has been so hit, and if they'd had a small nuclear reactor there, they wouldn't have had nearly the trouble that they did. So yeah, that's a good question, but I had to do the math with you. But you can see that, yeah, Wisconsin could certainly do a lot, and Wisconsin is improving, but we still are. I think it's 85% fossil fuels at the present time, and we'll probably always have a few methane plants because of the versatility, but we could sure cut them back a lot, and they could be supporting some of the solar panels. But sooner or later, and it won't be very long, all those solar panels that we're putting out at Maurice Airport and various other places around town, they're only going to last 20 years, and I've not heard anybody talk about replacing them. Nobody seems to put that into the equation. They just ignore it. But 20 years, something's going to have to replace it. And if they don't put in solar panels, by that time, maybe people will realize that small modular reactors would fit in there very easily, and then some.
You're gonna had a question, Marilyn?
Yes, I did. Thank you, Paul. One of the things you mentioned was that we needed education. Who would you say should be starting that discussion? Because I think a lot of people are concerned what they've heard about disposal and, tankers running through their communities, and, some of it's old information, but I guess who should be the initiating the education, and what kinds of things would you like to see done?
Thank you for that question, Marilyn. I think it's very appropriate to raise that issue. I'll tell you a little story by starting to answer that question. About 3 months before Tony Evers was voted and elected as our governor, I and my friends who built the website took the initiative to invite Tony to have coffee with us. And so we met him on the square and had a cup of coffee together. And he related to us, we asked him what his feelings were about nuclear energy. And he related that he grew up near the Point plant up in Lake Michigan, and he was very positively supportive of nuclear energy. And as we ended the discussion, it was a very friendly one, I said, I would love to have a picture of this historic meeting, but it's very dark in this room. Would you mind if I took your picture along with my friends out in front of the cafe? And at first he said yes, and then he said, somebody might take that picture and use it in a negative way, and I might lose the election. So I'm going to decline your kind offer to take my photograph associating with you pro-nuclear people. So that comes to your question in the sense that Tony right now is very involved in helping us through this dreadful pandemic. And I'm glad to see him doing as well as he is. He's got a lot of stumbling blocks, but he's making some progress. And I think we'll win, especially with the vaccine, help from the vaccine. Once that's over, I'm hoping that Tony can then come out of the closet. It's remarkable. We use that term coming out of the closet to talk about people who want to admit being gay or lesbian. But I think it's almost like people coming out of the closet to admit that they support nuclear energy. But I think as more people do, it will happen. And I think Tony will help us and many other people, but I'm only using him as an example because I've met him firsthand and I admire what he's doing. But he's an example. But we have wonderful people right at the university. The former chairman of the nuclear energy department is very active. He's been spending the last 10 or 20 years going around the world giving lectures on the reality of the accident in Fukushima. He studied it extensively and was part of a panel. His name is I'm having a little hard time remembering his last name, but it's something like Masadini or something like that, but I'm forgetting it at the moment. I apologize. Anyway, he is his replacement is very active also at the university, and he's teaching graduate students and promoting nuclear energy all the time. I think that is on the cusp of coming. I just get invited to webinars more than I can possibly attend on people from the industry, people from the utility industries, from the nuclear industry, educating and promoting these ideas. I just can't go to all of them fast enough. And I'm not an economist and I'm not a politician, so I don't go to all of them, but I make note of them and do sit in on some of the free ones to try and learn as much as I can about educating people. But that's why, in a little way, I agreed with Paul to come and talk to you folks, because I feel that by talking to you, I'm investing an hour or so of my time in hopes that you will, in an exponential way, tell your friends about what you've learned today. And so you're part of the equation.
On that, you showed your thing about the chain reaction. The two neutrons go off and trigger their reaction in others, and that triggers neutrons that go off and trigger the next one, and you have a chain reaction.
Yes.
And that's the way the fission plants work. But that's really like the way the virus works too.
Yes,
one
indeed.
Person's infected, they infect 2 other people who spread it to 2 other people, and you also have a chain reaction explosion.
Good point. And so we can apply that to the spread of educating the public.
I hope so.
Instead of getting infected, it would be, if you use the word infection, it would be with the bright idea, not a lethal virus. Very good.
Richard, oh, sorry.
Somebody else? Yeah.
Sorry,
I
I
don't-
thought you were done.
Okay, I had one more. I think that solar is sort of not efficiently utilized if people only think in terms of generating electricity. Now, it's not practical in Wisconsin, but down in the tropics, like we go down to St. Croix in the U.S. Virgin Islands,
Yes.
and relatively few people have solar water heaters, but
Yes.
it's not very efficient to be heating your water. Even if you want to use solar or anything, heating the water, generating electricity to heat the water when you could just heat the water directly. And I just kind of odd that more people in tropical climates don't put solar panels, solar collectors on their roofs or someplace where the sun shines all the time. They are used a bit in Israel and lots of times in Haifa, where we go sometimes. You'll see on the roofs, they'll have this tanks with solar collectors, and they just heat the water directly, usually facing east, so they get the hot water in the morning when they want to take a shower, and then up to midday, and then just heating the water. You don't have to worry about it freezing there, as you would here. So as I say, it would not be practical in Wisconsin. And I'm surprised you have solar panels on your roof, because it seems to me that solar is not good for much of anything in Wisconsin because you don't get enough of it.
Let me answer that one briefly, because I don't want it to hog too much time. But when I first went to Focus on Energy and they came and did an analysis of my house, I said I don't want to use too much of the roof, and I want to use south-facing roof and so on. So we had some limitations, and I suggested using half for passive solar for hot water and half for photoelectric. And they said, that's not a good idea. I said, why? And they said, well, because to run it to your water heater is at the far end of the house, and you'll lose too much heat just running it there. Far better to run the electricity. And they were right. So I did that. Now, so far as my installing them, my rationale was to learn primarily. I would say over 50% of the reason when I put those on in 2009 was to understand more about the good things and the bad things. And it taught me a lot of good things. It taught me that, and the Focus on Energy, which is a wonderful organization here in Madison, showed me how I could change some of the electrical appliances that I was using in the house and save as much energy by making those changes as putting on $12,000 worth of solar panels on the roof. And they were about equal. So what I did was I cut my energy consumption by 2/3, 1/3 of which was changing the appliances in my house, and the other third was from the photoelectric energy. Also, I managed to get a grant from Alliant Energy, although MG&E also had one, but I didn't get my electricity from them. And they paid me 25 cents a kilowatt hour for 10 years. And that allowed my investment in solar panels to pay for itself within 10 years. Otherwise, with the cost of solar panels back in 2009, it would have taken 20 years. So I'm grateful to the grant from Alliant Energy, and my solar panels have paid for themselves. And now I'm hardly getting anything out of them. But they offered to shut it off, and I said, no, I want to keep my measuring device on there so I can watch the slow, gradual decay of these solar panels and look at its change as the neighbor's trees grow up and as the sun gets lower in the horizon in the wintertime. And I can factor all these things in. I get all the information I want, and I can be an information junkie. So that's part
I was going to ask you about trees. It seems to be another big disadvantage for any kind of solar within the city of Madison is the trees. When we moved out here, this house was kind of out in a field on the west side, and we got a lot of sun beating down on the roof. It was even fusing the shingles together. In the meantime, we planted trees, the city planted trees. Every year the trees get bigger, and now most of the house is in the shade most of the time. Well, actually, from an overall, use of for us, it's better. I think the trees do more good for us than any electricity that was being generated by those panels. And these days, that's it's 40 years, 50 years later, the trees would have totally shut off any electric power, but they're also cooling the house as much as if they were running an air conditioner all the time.
That's probably true. I haven't done a math on that, but I live in an apple orchard. My address is Applewood Drive. And the apple trees do not shade the solar panels. They're not that tall. And the leaves are so small that they blow off with it when we get a nice brisk autumn wind. So I don't have to bother raking the leaves, and I don't have any problem with, or very little problem, except some of the neighbors' pine trees.
But
But
one other thing on solar, I see they're out in the fields around here. They're putting in these large
Yep.
solar panels covering the ground. And
Yep.
I'm thinking, how much electricity are they going to generate when we have a foot of snow and it covers them up? I can remember years, and whether we're getting these kind of years again, but many years when we first moved here, you could count on cross-country skiing around in the Arboretum or in the parks pretty much from Thanksgiving through Easter. The ground was, we get a good snow, it covers the ground and it keeps the ground covered for long periods of time.
we noticed that too. We moved here in 1980 and we used to keep snowmen in the yard all winter long and go cross-country skiing, and now you don't. If you go to Middleton, if you're driving north on Highway 12, you can see the roof of the Middleton garage there on your right as you're driving out of Middleton to the northwest. And on a wintry day, you'll see lots of snow, but you're very, very right. That there's not nearly as much snow as there used to be, would have been if they built those panels 10 years ago. So climate is changing, is doing some awful things to California, but it's making our solar panels a little more effective here. Yeah, I think
So,
Roz was.
Richard, I just have a quick question for you, I think. So are the most current or up-to-date plants, do they not create radiation? They don't create it as create as much radiation, or things are reused, and so they're because part of my question when you talked about fear is, okay, if a coal mine has a disaster, you have a couple hundred people that die, or if an oil well explodes, you have the people on the oil well. But as we saw with the Japanese disaster, it's not only that people die from the initial explosions and whatever, but the radiation goes into the atmosphere, in my understanding. And you had the equation there of deaths per kilowatt hour or whatever that was. However, there are other medical and effects of radiation that you don't have if there's a coal mine disaster or
That's right.
and at least in my thinking. So if you can tell me where my thinking is off, or where I missed the boat, that's what I would like to know.
Well, thank you for that question. It was really a good one. You ask a lot of things, and I'll try and be efficient in my reply. First of all, people have this fear that nuclear plants are putting out radiation all the time. And they have measured that. And then they have measured the amount of radiation in our bodies. We not only have these isotopes in the earth called thorium and uranium, these powerful things, but we have a thing called potassium. And potassium is a very important part of our bodies. It makes our hearts move, the heart muscle. And there's an isotope of potassium that is radioactive, and a certain part of the potassium in our bodies is radioactive. And they measured the amount of additional radiation that an individual gets by sleeping next to their partner or anything like that. And it turns out to be more than the radiation that you get from a nuclear plant half a mile away. And so as long as you're married or otherwise living and sleeping next to somebody, you're getting more radiation from your partner than you're getting from a nuclear plant. Now, to your question about Fukushima, that's an interesting story because nobody died of radiation in Fukushima. Some people claim that maybe a few people got thyroid cancer, and they neglected to pass out normal iodine to people so that they would not be taking up radioactive iodine that was in the air. But in spite of that, they haven't been able to prove that thyroid cancer had a higher incidence in that area of Japan. And so there's all of the deaths in Fukushima were from either the tsunami or the suicides. Now we come to the suicides. The company that ran that utility is named TEPCO. It's a private company that stands for Tokyo Electric Power Company. They made a lot of bad decisions, a whole bunch of bad decisions. but focusing mostly on the people, they did not provide any support. They lost the confidence of the people by giving out half-truths and outright falsehoods to try to keep the people from getting frantic. And by so doing, they made a lot of mistakes in people, and they also moved way more people, about 10 times more than they needed to remove them from risk. There's another utility just north of Fukushima with a different name, and there's a plant there called Azagawa, and that is closer to the center of the earthquake zone, underwater earthquake, than Fukushima was. And they managed very, very differently. First of all, they were smart enough to build their plant 25 feet above the high water line, and it was within the limits that were recommended, because Japan knows a lot about tsunamis. They've had them for thousands of years. And it was only at Fukushima that they built it down low. Up at Ozagawa, they built it properly. On top of that, the utility opened up the plant right after the tsunami and offered protection for children and families of people who had lost their homes, and food and shelter, which was not, of course, done at Fukushima. They couldn't begin to, because they were having, over the next week, all kinds of problems with the escaping hydrogen and so on. But by building the plant properly and by reacting properly with their customers, the total attitude and reaction in Ozagawa was entirely different from Fukushima. And when did we find out about that? About a month ago. The press totally ignored it. I'm just finding out about it now. So that tells you a lot of things in answer to your question. But I think we have really magnified the problem, because the news media love stories. They sometimes tell us good stories, but in that example of Japan, they totally overlooked the good story and only told us for 20 years the bad stories. And I think that's a shame. It gave the whole public a wrong idea. Now, so far as an explosion is concerned, the only plant that exploded was the one in Chernobyl, and that was not a nuclear explosion. It was a pressure explosion, because they did not have a containment dome, the only reactor built in the world without a containment dome. And they were using graphite as a moderator, and only Russia for quite a while was using those kind of moderated reactors. They're no longer using them. They've gradually shut them all down. And so that relates only to Russia, and that was sort of an experimental but commercial reactor that was being used. It was destined to happen from, if you look back at all the rules that they broke. And yes, about 50 people died. And some of them were told to, and some of them volunteered to go in and clean up that reactor, and died, I think, perhaps half knowing that they were risking and giving their lives to the country in doing that. So it's a real tragedy, but again, oftentimes exaggerated. And sometimes people have gone back and showed that the wolves are thriving there today. And there are very religious groups of Greek Orthodox people, I think, or Russian Orthodox people, have come back in to the churches there, mostly elderly people, but they're doing just fine. And so it's a strange thing what we are told and what the truth really is. And I think we have magnified the risk from nuclear out of sight. And when people come along and show us that the potassium in our bodies is giving us more radiation, let alone the cosmic rays and the amount of exposure we get getting into a jet and flying from one end of the country to the other, is greater by far than anything you're ever going to get from a nuclear plant in your whole lifetime, then we realize that nuclear plants really aren't that dangerous. Also, we have sometimes built buildings from a special steel that was contaminated with radioactive cobalt. And they didn't realize it at the time that there was some radioactive cobalt, but later on they realized it. And so they went back in and analyzed the people in that plant for cancer or other radiation effects, and found that there was less cancer or about the same amount, and they lived longer. And so people can argue that because human beings evolved at a time when there was much more natural background radiation in the rocks than there is today, that maybe a little bit of radiation is good for us and stimulates the immune system. And people are coming up with the idea of using very low dose radiation, not just to prolong their lives, but perhaps to treat better the pulmonary disease in people with COVID infections. And so I'm aware of this, of course, in my field as I read about the literature of radiation oncology and what tiny doses of radiation might be doing for us. And there's a name for this. It's called radiation hormesis, HORMESIS. And I would say that the world is divided among physicists as to whether radiation hormesis exists or not and how effective it is. I'm inclined to believe that it's a likely possibility, or even perhaps probably true, that as we evolve the radiation background that we had, we have very efficient repair mechanisms. And if anything, it may aid our long-term health.
That reminds me of when I was a kid. They would sometimes go. I think it was either Hot Springs, Arkansas, or Mineral Springs, in Missouri. I think it was Hot Springs, Arkansas, where they actually had some water baths that had a little bit of radium in them, or radon, and they would bathe in the radon on the grounds that exposure to the radioactivity was a good thing for you. And this was this was way back in probably the 1940s or something.
That's right.
But that was thought.
Well, it sounds like you're saying that the effects of radiation are negligible.
Yes, in a word, you summarized it very well. Yeah.
I guess I find that hard to believe with the effects of, and maybe this is from back in the original stories where they had deformities and cancer and other kind of diseases that people were impacted by long after the original disaster itself. So I guess I have to think about that.
Sure. Well, you do.
I think it's like wine. One glass, a little bit is really good for you, but too much of it is bad for you.
Absolutely.
And that's my point. And that's my point.
Oh, yes.
If you're living by it and you say it's negligible, I'm talking about when there's something doesn't go right, and
Sure.
it's not just the negligible part of it.
Yeah.
I understand that, Jim, and that's not what my question was about.
Yeah, I appreciate that. I think that people talk about lethal meltdowns. Well, in the world, there have been only two meltdowns that real significant meltdowns of any kind. One being at Chernobyl was not a meltdown; that was an explosion.
Right.
But 3 Mile Island and Fukushima were both meltdowns, and to the best of my knowledge, nobody died at either of those. So the idea of a lethal meltdown hasn't happened yet. On the other hand, let's look at radiation for a moment. I'm very aware of irradiating children and the care that people would take of that, but especially embryos. If a woman is pregnant, particularly in the first third of her pregnancy, she should not go anywhere near an X-ray machine. And we don't allow our technicians during the first 3 months of pregnancy to come near our accelerators. So that is a very sensitive time in human development. But unless we happen to be an embryo within the first 3 months or so, things are not nearly so sensitive. So the formation of the embryo, there are different parts of human life that have different levels of radiosensitivity. At our age, we are getting far more exposure from just the occasional X-ray that we're getting for mammograms or for chest X-rays. And when we get a CAT scan, we get quite a lot of radiation, but still not enough to hurt us in any way, and that we're aware of. And we've not seen any evidence in the literature to suggest so. But there's another tiny little story that I'll share with you, and that is the history of Wilhelm Conrad Röntgen, who discovered X-rays back in 1896. And he noticed, of course, that things were luminescing and fluorescing at a distance because of these rays that he didn't understand, that he called, or were later called, X-rays. And when people in the United States heard about this, particularly young people who wanted to look after somebody who came into the office with a possible broken arm or broken leg or hip or back, they would use back about almost 100 years ago now, around 1920, they would have fluoroscopes. And these were primitive X-ray machines, and you'd have to warm them up for a little while. And so they would come into the office in the morning and turn on the fluoroscope, and they would check after, by the time the first patients would start coming in, they checked to make sure it was sufficiently warm by holding the fluoroscope in one hand and putting their own hand in front of it, the opposite hand in front of it, to see how it would show up on the screen and make sure that it was warmed up properly. They did this every morning, 5 days a week for years. And many of those early radiologists developed malignant, very bad skin cancers of that hand, which then metastasized to their lungs and killed them. And I wrote up about this when I was in medical school as an essay on how Conrad Röntgen always protected himself with a lead apron, but the people who learned from his discovery how to use X-rays in their practice were not as cautious as the discoverer. And they themselves were martyrs because they didn't understand and take proper care of themselves. So X-rays can definitely induce cancers, particularly if you do it every day for a long period of time professionally. It's a dangerous thing. So, yeah, you can't just say that radiation is innocuous. It depends on how it's given.
I remember when I was a kid in the shoe stores,